and then use your phone. You can scan all the pages in and then email it to yourself.
Okay, so welcome to people who are joining on YouTube. We were just talking about submitting homework and how there's an app called Genius Scan that lets you scan in every page of your homework and put it all into one PDF document, and then you could submit that one PDF to Foxtail. I do think that that's a better way to go if you can combine all of the pages of your homework into one document. It's certainly going to make it a lot easier for whoever's grading it. And we'd like to get you good feedback and not like put feedback on like 6 different documents. So yeah, if you could combine everything into one PDF, that would be excellent. So, yes, sir.
Would you mind, the one thing that I would prefer is when I was watching the live feed on Friday, you asked, would you like me to continue? And I said, I was like, yes, please. But you kind of stopped the problem, and I understand.
Oh, and you on the chat, you said that?
No, I didn't. I just said it out loud.
Oh,
like, please continue.
Yeah, and then I stopped.
Yeah.
I'm a terrible person. But no, that's good. I think I will sort of watch to see if somebody put something into the chat. So if you do want to and you're on the YouTube feed, feel free to just say, yeah, please keep going. I didn't hear you.
I wasn't watching it live.
Oh, yeah. So in general, I mean, it's a give and take anytime you have 50 minutes, right? So it's kind of like, do I show you how to set up more problems, or do I do like 3 in full detail?
Sure.
I try to do a mix. So, yeah. Any other, so let's get started. Any homework questions that I can answer over 6.3? Yes, sir.
58.
58. Okay. So we're in our section about volumes by slicing. The question was over 58. In 58, we're taking some region and revolving it around some line. So 58 says we've got y equals x. We've got y equals 1 plus x over 2. And we have y equals around about y is equal to 3. And let's see. So y equals x and y equals 1 plus x over 2. Okay, well, let's take a look at it. My first instinct is not great on this, but we'll see. Okay, so y equals x is just our next line like this. Y equals 1 plus x over 2. So we have a y-intercept of 1. And then we have a slope of 1/2, meaning we go up 1. By the way, this is 1. So we go up 1 and over 2 here. So the question is, did they want us to use the y-axis as one of the? Y and y equals 1 plus x over 2 about y equals 3. Let R be the region bounded by the following curves. Find the volume of this function. feel like they,
Could it be the triangle created from a line?
well, it makes a lot of sense, right, for it to be this triangle, right? So if they would, what I was looking for, that's why I've read the problem about 4 times now, is I feel like they wanted to say like in the first quadrant, or that we need another line like it's bounded by the axis or something like this. It doesn't, if it was all of it, well, that's easy. It's infinite. Okay, so if we are revolving that, so that's not it. So the question is, well, what is it? That's a good question. They didn't do a good job of, but let's assume that they're trying to break it here and just we'll do it, and then I can check that answer later. Maybe I have these answers in the back of my book. I'm not sure. Let me see. It's not looking good. No, I don't have the even answers. Okay, but I mean, we'll get this right. Whether or not it's what they wanted, we will see. So let's say that we cut it right here, and then they say they want to revolve that around y equals 3. So y equals 1, y equals 2, y equals 3 is right here. So here's the line we're revolving around. And so when I spin that thing, what will it look like? Well, let's see. So it will look sort of like, we've got like a big circle and then a smaller circle. Like this. And then it kind of like comes into a point. Okay, so this is what the shape would look like. And now the question is, what is the volume of the shape? Now, it's fairly clear that if I just take a cut down the middle of this thing, what's the shape that I get? A washer, yes. A washer, so if I slice this thing, I get a nice washer, right? So we need to use the washer method. And the washer method tells me that my volume should be equal to the integral from. Okay. So if you watch the videos, I probably talked about like chopping this thing up using like a butcher's knife, right? And so if I were going to chop this thing up into washers and I started cutting it, then what axis would I be cutting? The x-axis or the y-axis? Yeah, the x-axis, right? The x-axis would get sliced by the knife as I was cutting this up into washers. And that doesn't seem as important right now, but as soon as we start talking about the shell method, this is going to be more important. So as I cut with my knife, I'm cutting up the x-axis, which tells me that everything that goes inside of my interval should be x's. Okay, so I need to use x stuff for the function. And what I want is, the formula for this, right, is pi r squared, but since it's the washer method, it's pi times the outer function squared minus the inner function squared. Okay, so let's plug this in. So I've got pi just hanging out. And then I have the outside function squared. Now this is kind of interesting. Because, and when I say the outside function, I mean like the radius, right? The radius of that washer. So like if we take this outside washer out here that we can see, the outside radius is that distance. Right? If I come back over here, what I'm talking about is the distance from this middle line that goes down the center of this thing to what's actually like the bottom function, right? But that's the distance I want to square. So if you just put in this function, y equals x, that's wrong. Because that's not the distance that I want to square. So the question is, what is that distance? Yeah, 3 minus x, right? Because 3 is from here all the way to here. And then this distance right here is x, correct? So 3 minus x is that distance. And that's what I want to put in. So here I'll put in a 3 minus x, quantity squared, minus, now we need the inner radius. So the inner radius is like from here to here, this distance, which if I come over here is from like here to here. So it's similar, it's 3 minus something. Well, whatever this function is, right? So it's 3 minus this function, quantity squared. So we got 3 minus the function 1 plus x over 2, quantity squared dx. So then I've got a pi r squared minus a pi r squared. And it makes good sense, right? What's pi r squared? When we typically think of pi r squared, what do we think of? Yeah, the area of a circle, or if you like, the area of a disk, right? So when we're taking a pi r squared minus a pi r squared, it's kind of like we're taking a disk and subtracting a disk, which makes a lot of sense. That's exactly what we're doing, right? Okay, so now we're ready to go here. We could keep going, finish the, oh, I didn't put in my limits of integration, did I? So where do we start cutting and where do we stop cutting as we cut this up into washers? We start cutting when x is what?
0.
Yeah, 0. We start here and we cut until we get to this point, which is 2. So we're integrating from 0 to 2. And notice that 0 and 2 are both x values because when we chop with the knife, we're chopping up x, the x-axis. Make sense? Okay, now let's do a little bit of work. Pull out the pi, it's a constant, and then we get integral from 0 to 2. We could square this out. If we did, what do we get? Does everybody know kind of the quick way to square something like this? Square the first one, you get 9. Then you get 2 times the first times the second. So 2 times 3 is 6 times a minus is minus 6x. And then you just square the second one, which is positive because it's squared, x squared. Okay, so I squared that one out. This one is a little more fun, right? Minus, if I square this out, 3 minus 1 is 2. And then I get a minus x over 2. Maybe we should have rewritten that, but I'm just going to write it up above just to remind myself so I don't get confused. I've got a 2 minus x over 2 quantity squared is what I really have in there. So if I do the exact same thing, 2 squared, otherwise known as 4, 2 times the first times the second. So 2 times 2 is 4. 4 divided by 2 is negative 2x. Right, that's 2 times the first times the second. And then the second one squared is positive x squared over 4 dx. Now we can combine like terms. I get pi times integral from 0 to 2. Let's see. I've got an x squared minus a fourth of an x squared, which I suppose is 3/4 of an x squared. I've got negative 6x plus 2 more x's. So that's minus 4 x's. And then I have 9 minus 4, which is positive 5 dx. All right, now we are ready to take the antiderivative. We get pi times. Antiderivative of 3/4 x squared, I bump up, divide by 3, so I get 1/4 x cubed minus 2x squared plus 5x evaluated from 0 to 2. Okay, that is equal to pi times, all right, if I plug in the 2, I get 2 cubed is 8, divided by 4 is 2. If I plug in 2, I get 2 squared is 4, times 2 is negative, we get minus 8. 2 times 5 is positive 10. Okay, all that minus, plug in 0 and I get 0, minus 0 plus 0, 0. So let's see what we got here. 10 plus 2 is 12, minus 8 is 4. So we get 4 pi. All of this provided that we actually were cutting this off right here, right? So if that's what they meant, which is all that I can assume that they meant, because if they didn't mean that, the answer is trivially infinite. So I'm guessing they did. Any questions on this one before we move on to a new question? Okay, another question. Yes, sir.
We can do 36.
36, sure. Okay, so 36, we've got y equals absolute value of x, and y equals 2 minus x squared. And we want to revolve that around the x-axis. Okay. So first of all, y equals absolute value of x. This pen is getting a little uncooperative. That's a little. So y equals absolute x is this, right? So there's y equals absolute value of x. Y equals 2 minus x squared is a parabola. It's facing down, and it starts up at 2. So it's kind of this kind of thing. So we've got what's trapped in between is right here, correct? And then we want to spin that shape around the x-axis. When I do, I get an interesting shape, that's for sure. Let's see, if I just spin the middle, so to speak, that's bad. Better. I do this, this. Ooh, that is interesting. So then it's kind of open, right? This is. Hey, done better. Getting picky. That's pretty good. And then this goes in to sort of a point in the middle. That's good. Okay, so if I cut it, like let's say right here, then I'd get and that shape is a washer. So we can see, yeah, we're definitely in the washer method, where the outside function, so to speak, is the parabola, and the inner function is the absolute value. Now, absolute values are kind of a pain, right, to deal with, but the way that I can deal with this one, there's a couple ways I could go. One way is you could just deal with it as two different functions. Like this one is y equals x, and this one is y equals negative x. That works. The other way that I could do it is I could notice that this thing's exactly symmetric, right? So if I cut it right down the middle, I would have half of it. So why don't we just forget this side, just spin this side, and then double it? So instead of integrating from, let's see, this is probably 1, correct? And this is -1. Instead of integrating from -1 to 0, and then from 0 to 1, let's just integrate from 0 to 1 and double it. And we'll get the job done because of the symmetry. Okay. So let's do it. So the volume is going to be, we said we were going to double something. So 2 times the integral from, we're just going to do the half, so from 0 to 1, of pi outer radius squared minus inner radius squared. So pi times the outer radius. In this case, the outer radius that I'm talking about, if I'm in here at this washer, is from the middle, which is the x-axis, up to this function. Over here, that's from here to here, which is just this functional value. So I just need to take 2 minus x squared and square it. So 2 minus x squared squared minus. Now we need the inner radius, which is from here to here, this distance, which on this one is from here to here, this distance, which is just, I guess I'm between 0 and 1, so from here to here, which is just the absolute value of x. But if x is positive, the absolute value of x is x. So I don't need the absolute value sign. I can just drop it because all of the x values are positive. If I was going from -1 to 1, that wouldn't work anymore because I'd have some negative x values and I'd have to account for them. But because we are clever, we just write x squared dx. Yes, sir.
Wouldn't it go away anyway because there's a square?
Because if you said absolute value of x squared,
X squared.
So to speak, I mean, as soon as you say absolute value of x, it's positive. But what I'm saying is like, well, what if you just don't want to deal with, so you're saying that the absolute value of x squared is x squared.
Yeah.
That is true.
Okay.
But yeah, that is true technically. I don't know if like that's a nice formal thing that's going to help you out of this situation in general, but in this case, that does work. Yes. Okay. So let's do some work. I'm going to pull the pi out of the integral because it's a constant. And so I get 2 pi times the integral from 0 to 1. I square this out. So 2 times the first, square the first thing is 4. 2 times this one is minus 4x squared. And then I square the second one and get plus x to the fourth minus x squared, all of that dx. So I'll simplify it just one more time. I get 2 pi, integral from 0 to 1, x to the fourth. I have a negative 4x squared minus x squared, which is minus 5x squared. And then I have plus 4, all of that dx. Now I'm ready to take an antiderivative. 2 pi just hangs out. Antiderivative of x to the fourth is x to the fifth over 5. Antiderivative of negative 5x squared is minus 5 x cubed over 3. And then we get plus 4x, evaluated from 0 to 1. Okay, now we're ready to plug these in. This is equal to, plug in the 1, and I get 2 pi times, plugging in 1, I get 1/5 minus 5/3 plus 4. And plugging in 0, I get 0, right? Everything just goes away. So that's it. So I still have my 2 pi. And then I actually have to think for a second. I guess my common denominator is 15ths. So 1/5 is 3/15 minus, let's see, 25/15. And then plus 60/15. So I still have my 2 pi. What do I got here? So 60 minus 25 is otherwise known as 35 plus 3, 38 over 15. And then I multiply that by 2 pi. So I suppose I get 76 pi over 15. And then the question is, can I simplify that anymore? I don't think so. That looks pretty good to me. Sound good? Any questions? Any questions from anyone on YouTube? Not right now. Okay. Yes, sir.
Could you do 34?
34?
Yes.
Sure. Okay. Try for a better pen again. Still just okay. Okay, 34. We have y equals the square root of y. I'm sorry. So 34. Got y equals the square root of sine of x. We've got y equals 1. We have x equals 0. And we're revolving around the x-axis. Okay. So, y equals the square root of sine of x. Well, how does sine of x, let's see. So let's do the other two first. So x equals 0 is just the y-axis, right? Y equals 1 is up here. And then we have square root of sine of x, which kind of does this sort of thing, right, for a little while at least. But what is, it actually keeps going, right, and does some other things over here. but I don't care so much because this is the region that's bounded by all three. Here, here, here. So we're talking about that thing. All right, so now that we've got our little region, we want to spin that around the x-axis. And when we do, what shape do we get? So on this side, it's sort of just a flat, round disc that kind of comes out a little ways, but then that kind of sinks. That kind of sinks in this way, like that. So it's kind of like you've got a cylinder and we carved out a bowl out of the middle of the cylinder. Seem reasonable? So if we were to cut down the middle of this thing, we'd get this, 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 a nice little washer. All right. Okay. My search is still continuing for a good marker. Oh, that's very good. Okay. So we want to do the exact same thing. We're still doing the washer method. So we are going to take the integral from, in this case, we're chopping washers this direction. So the x-axis is getting cut when we make our cuts with the butcher knife to make our washers. So we're going, where do we start cutting and when do we stop cutting? We start cutting at x equals 0 and we cut until we get to x equals what? Yeah, what's this point where sine is 1? So sine of what, pi over 2? Yeah, sine of pi over 2 is 1, square root of 1 is 1. So this is pi over 2. So we're integrating from 0 to pi over 2, 0 to pi over 2 of pi times the outside radius. So the outside radius in this case, the middle is the x-axis, and the outside is all the way up at the top. So if I'm looking at it over here, it's starting in the middle and going all the way up to the top. Well, what is that distance? Yeah, that's just 1, right? And it doesn't matter where I'm at across the shape, it's always 1. So this is just, the outer radius is just 1, I suppose, squared, right? Minus the inner radius, which is starting in the middle and going to this point. But that's the function. And in this case, the function is the square root of sine of x. So I get minus the square root of sine of x squared, all of that dx. So again, the pi can come out. I get integral from 0 to pi over 2 of 1 minus the square root of sine of x squared is otherwise known as sine of x dx. Okay. Which is equal to, the pi stays there. Antiderivative of 1 is x. Antiderivative of negative sine of x is what? Positive cosine, right? Positive cosine. So this is plus cosine of x evaluated from 0 to pi over 2. Now we can plug things in. Pi hangs out. Plug in the pi over 2 and I get pi over 2 for the x. And then cosine of pi over 2 is otherwise known as 0, right? So plus 0. Minus, now I want to plug in 0, which gives me 0. Plus cosine of 0 is 1. Okay, which is pi times, well, I guess I've got pi over 2 minus 1. So pi over 2 minus 1, or if, and now it's just like a matter of preference on how you want to write this. It all seems equally terrible, but you could write this, I suppose, as pi squared minus pi, this one over 2, or you could do some fancy thing like pi squared minus 2 pi and get a common denominator over 2. All of that's right. Okay, so this one would be adequate, and that one is too. Sound good? Any other questions? I think something that you'll definitely see as we go along here is that it's going to be very advantageous to you to watch the lecture before you come. Okay, I don't know, maybe some of you did, maybe some of you didn't, but if you didn't watch the lecture before you come, I could see how this could be kind of like, what's he talking about? I didn't really watch the video, so I'm not exactly sure what he's talking about. But so that's going to be a big deal when we're doing this model of class, is definitely watch the video for the next section before you come, like on Wednesday, for example, so that we have something to talk about and you know what we're talking about. That's very good. Any others you'd like me to work through?
Would you mind doing 29, please?
Sure. 29. Okay, 29, we have y, 29, we have y equals cosine of x. It says on the interval 0 to pi over 2, y equals 0, x equals 0, and we're going around the x-axis. All right. So first, let's do our best to draw this thing. So y equals cosine of x starts up high and kind of comes down to here and hits 0 at pi over 2. And then we've got the y-axis. Well, y equals 0 is otherwise known as the x-axis. X equals 0 is the y-axis. So this is our region we're talking about. And then we want to take that region and spin it around the x-axis. So if we do, we should get a shape sort of like this. And that's it, right? So if we cut it, we would get this shape, which is a nice, in this case, not a washer, but a disc. Yeah, we get discs at every cut. And so this one is a little bit easier to set up since we don't have to use an outside function and inside function. We can just use the one radius. Okay, so in this case, we're integrating from 0, and remember, where are we cutting? To get discs, we cut the x-axis. So we're starting at 0 and we're cutting disks out until we get to pi over 2. So we're starting at 0 to pi over 2 of pi r squared. So we put the pi in, pi. And then the radius in this case, if I look at my sample disk right here, here's the center, which is on the axis, right? And so really, I'm just looking at the functional value. We're over here from here to here, whatever that is. Well, that's cosine of x. So I get pi times cosine of x squared dx. All right, again, I can take the pi out, and I get pi integral from 0 to pi over 2 of cosine. I could write this as cosine squared x dx, that's the typical. And now we're in an interesting situation where we have to remember a trig identity. And I think they're even nice enough to tell you, right? What's it say? 29, it says, hey, hint, recall that cosine squared of x is 1 plus cosine of 2x over 2. That seems very relevant. The reason being is I don't know what the antiderivative of cosine squared of x is. And if you think about it for a minute, you think, okay, I need something whose derivative is cosine squared of x. It's kind of like, yeah, I don't, right? So this is helpful to have our half angle identity to help us out here. So we've got pi times integral from 0 to pi over 2. And now they say the half angle identity says that cosine squared of an angle, or cosine squared of x, is 1 plus cosine of 2x all over 2 dx. Now, if I wanted to, notice this whole thing is multiplied by a 1/2. So I could pull that 1/2 out with the pi if I wanted to. Why not? So I'll pull that 2 out and get pi over 2, integral from 0 to pi over 2 of 1 plus cosine of 2x, all of that dx. Okay, now I'm ready to take an antiderivative, and I have something that I can take an antiderivative of, which is good. Okay, so this guy is equal to, I still have pi over 2 on the outside, and then I need to take an antiderivative. Antiderivative of 1 is just x. And what is the antiderivative of cosine of 2x? Almost. You had the right idea, but you were thinking derivative. Well, okay, so you said sine of 2x, right? So the sine part is right. And the 2x part is actually also right, but the 2 times is not right. Yeah. Divided by 2. That's right. Yes. So this would be plus sine of 2x over 2. And then that's going to be evaluated from 0 to pi over 2. All right. Okay. Now we're ready to plug things in. We have pi over 2. Plug in the pi over 2, and I get pi over 2. And then plugging in pi over 2 for x here, I get pi over 2 times 2, which is pi. And then sine of pi is what? 0. Yeah, sine of pi is 0. So this is plus 0. Then I plug in 0. So I subtract, plugging in 0. X is 0. Sine of 0 is what? 0. Yeah, so plus 0. So that's it. So we end up with all we have is pi over 2 times pi over 2. So that, I guess, is pi squared over 4. And we're done.
It's not anticlimactic.
What's that?
That was kind of anticlimactic.
It's true, but it's okay to get a bunch of zeros. Makes life easier. Okay, other questions? Are you feeling like you're getting the hang of this? Yeah, I think, again, the things that will kill you in this section and actually in the next section, and actually in calculus too, is if you don't know your unit circle very well, that can be hurtful. So if you don't, I have a couple videos on YouTube about that. I'd watch them. Yeah.
Are you gonna have this want us to memorize the trig functions or the trig identities?
Oh, you mean like the half angle identity?
Yeah.
If I do have something like that that I want you to memorize, I'll let you know. As of right now, you don't need to necessarily memorize the half angle identity. It will come up a lot later, and eventually you probably will want to learn the half angle identities, but the only ones that I really expect you know off the top of your head is like sine squared of x plus cosine squared of x is equal to 1. That's a very common trick that comes up in calculus all the time. And if something else comes up, I'll let you know. So, but you definitely need to know the values. That's really important. Okay. That seems like a good place to stop then. Yeah, have a good day. I will expect, so homework is due today, correct? Okay, am I thinking correctly? Today over 6.3?
Yeah.
And then it's due Friday over 6.4.
Yeah.
So that gives us 2 days of questions over 6.4. So come on and feel free to bring questions just about the lecture too. If you're kind of like, hey, I didn't understand a certain part, would you explain it again? That's great. But we will have 2 days over 6.4. So Wednesday we'll fully devote to section 6.4. And then Friday will kind of be like any last questions on 6.4. And then maybe we'll move into some questions on 6.5. Sound good? Okay, have a great day. I'll see you on Wednesday.
Oh, I have a question.